So we always draw chemical reactions as like basically it's in white, like a linear reaction. I don't like that they wrote that, but basically we just go Na plus Cl minus goes to NaCl. Now that is a very simple reaction, but we write every reaction right like that in a single step. The reality is they're not like that, unless it's like a two-particle collision, two atoms in this case, two ions. Okay, but if you look at this one right here, 5C2O42 plus permanganate plus 16 protons, blah, blah, blah. There's 23 things there that need to react. The odds of them coming together in a perfect collision all at once are basically zero. All right, that's 23 particles that have to come together with the right kinetic energy and the right geometry. That's not going to happen. So things go in steps. Okay, so it's almost zero. Even if you look at the three-particle collision of two hydrogen molecules plus oxygen, all right, it's not going to happen in a single step, all right, because it's 1,000 times less probable than a two-particle collision. This, fairly straightforward. This is 1,000 times less likely to happen in one step, just by adding an extra particle or molecule. No, it's going to depend on the molecules and stuff, right? But it would scale. Okay, I don't know the exact scale, but it would scale. All right. So most things occur in a series of simple steps. It gets broken down. Now some happen really fast, some steps are slower, etc. We call this reaction mechanisms. All right. And if you look in textbooks and you look in other Chem 12 class notes, they all kind of use the same reactions because you have to study these reactions and they're not easy to study and isolate the intermediates and stuff. All right. So a lot of mechanisms, we don't know how they work. So each step is called an elementary step. Oops. And so for this is how we would write this reaction. That's how you're used to seeing it. 4 hydrogen bromides plus oxygen gives you 2 water molecules and 2 bromine molecules. All right. But what actually happens is one hydrogen bromide reacts with 1 oxygen molecule. That's a 2-particle collision. Okay. You get this HOOBr. Then that molecule reacts with that other hydrogen bromide to give 2 molecules of 2HOBr. And then those 2 molecules react with the final 2 hydrogen bromides to give your final 2 products of water and bromine. Okay? These things right here, which form and they form in one step and then they're used up in the next step, are called intermediates. Okay? They form and then I'll say and then are used up. They are not seen in the final reaction. Okay? They're just part of the steps that happen. So the first step here is the slowest step. Okay? The slowest step in the reaction is called the rate determining step. So I'll say RDS for short. What happens to the rate if I increase the speed of step 2 or 3? If I speed up step 2 or 3, what happens to the overall rate of the reaction? Sorry? It doesn't change. The only way to speed up the rate of a reaction is to change the rate determining step. Because it doesn't matter if I speed these two up, this is still the slowest step. Okay, so that determines the overall rate. So okay, so you have to speed up the rate determining step to have any effect on the overall rate of the reaction. Are we good? All right. So here's a reaction, made up molecules, A's and X's. 3 steps. A plus 2x goes to AX2. AX2 plus x goes to AX and X2. And then the AX and the A form A2X. What's the overall reaction? It's like math, people. Look at the look on your face right now. So you cancel. If they're on opposite sides of the reaction arrow direction, I don't know what you want to call it, they cancel. So that cancels that. This cancels this. Anything else that will cancel? This X will cancel that X. A and A? Nope, those are on the same side, right? They're on this side of the arrow. So what is the reaction? This A and that A, that means there's 2 A's plus what? 2 X's forming A2 and X2. It's just simply canceling stuff out. Just like math, except you don't have to do any math. Okay, well, I guess we added, but. Nope, this is a molecule. This is simple as X atoms, whatever that is. We'll do one with, well, we'll fill in the blanks here. Okay. So a classic question on a test or a quiz. You want me to repeat that? A classic question on a test or a quiz is the following. Okay? You're given a couple of steps of a reaction mechanism, and the final product, you got to figure out what's missing. Okay? So, what doesn't appear in the final reaction? What letters? The C's need to all disappear, right? Everybody agree with that? Okay. So, here we go. So this C3 is going to cancel that. I need this C2 plus to cancel out. How do I make that happen? Well, yeah, you need to put it on the other side of the arrow, right? Because then they'll cancel. Okay, so then that cancels that. I need this C4 plus to cancel out. Where should I put that? Other side. Okay, so then that would cancel that. Okay. All right. Now, I have 2 A4 pluses. Look, I apologize for the formatting here. It's not great. but this is A4 plus. This is the same as this, and it should be a +4. It's a charge on it. 2 A's, 2 A4 pluses. So we're good, right? I need to have a B plus. Where, like, there is no B's. So what do I need to do? I need a B plus or B positive. A B positive on that side. All right. A3 and A3 gives me 2 A3s. So what else do I have to have here? A B3 plus. That's the missing step. And then check it. Okay? Once you write it out, check it. So C2, this C2 cancels that C2. This C4 cancels that C4. That and that are gone. So 2 A's, a B gives me 2 A's and a B, and we're good. What?
How would a C just disappear from the equation?
How would a C disappear?
Yeah, like if the reaction were to show up.
What do you mean disappear? I don't understand.
Oh, you get C. I'm thinking of C as like an individual atom.
No,
It would be a molecule of a combination.
yeah, it's some molecule or whatever. It could be an atom that shows up and then.
It can just leave.
Well, yeah, I guess it's best if we just think that these are just molecules.
So it'd be like a molecule.
Yeah, so it gets converted. Yeah. Well, here's a real reaction right below it
Yeah.
instead of using these. Okay. All right. So let's do this one. This is an actual real reaction instead of just A's and B's. Okay. Final reaction. Again, the formatting is horrendous here. Chloride, Cl2, trimethyl chloride, trimethyl chloride, and hydrochloric acid and carbon tetrachloride. Okay. So Cl2, Cl2. So we're good, right? Nope. Okay, so this needs to cancel. CCl3. That needs to go away, right? Because it's nowhere in the final product. So what do I have to do? You have to put it over here. CCl3. Shh. What else has to go away? The Cl, right? This Cl will cancel that, but we still have another one sitting there. So I have a chlorine there. What else do I need? An HCl? Is that what you're saying? Yeah, on this side, right? I need an HCl. What else? CHCl3. And then check it over. So we go CCl3. Whoa. Don't need it to be that big. CCl3, CCl3. Cl. We get Cl2 plus CHCl3 goes to HCl and Cl4. There you go. Okay. Is that okay? Yep.
When you had the CHCl3, like you added it to the second step, does it matter which one?
Which
step you added to, as long as it's on the same side?
Well, this is the step that we're filling in.
Oh,
Right? It's the blank step. So I'm asking you to fill in the step.
add them to,
No. If I give you a question like this, step 1,
okay,
step 2, step 3, because we only want 2 particle collisions, right?
yeah.
Because 2 particle collisions are the most highly probable. Are we good? Shh. Okay. All right. So reaction intermediates, we talked briefly on the previous page, is a species, an atom or a molecule or an ion which is produced in one step and used in the later step. In other words, it appears on the right side of the equation and then later on the left side. Okay, this is important because not all things will, if it appears on the right side, then the left, it's a reaction intermediate. A catalyst is different, okay? And we'll talk about catalysts in a sec. So, in this reaction, what are the reaction intermediates? So, HOOBR and, whoops, and this, okay? So they have to form on the right side, and then in the next step, or one of the next steps, they get used up on the left side, okay?
Do we include the coefficient?
Because it's the molecule they're asking for. What? All right. Intermediates don't accumulate, okay? Because as soon as it's formed, it gets used up again. All right? That's not mine. They're not unstable. They don't have to be unstable. Some will be, but not all are unstable. They get used up again because the reaction is going fast. Okay? All right? They're different than the activated complex. The activated complex is unstable and short-lived. Intermediates form. They're stable molecules, but they get used up in the next step because the reaction is speeding along. Okay? Are we okay? All right, next page, please. All right, so what does a reaction or potential energy diagram look like for these things? Basically, it's the number of bumps. It increases the number of bumps because it goes in steps. It's like a bunch of different reactions, okay? A couple things that are important here. So the highest bump is the rate determining step, okay? It has the highest activation energy. That's why it's the slowest step. No. No. Sometimes the slowest step is the second step. Doesn't have to be the first one. Yes. The rate determining step. All right. The overall forward reaction, or the energy of activation for the overall reaction is basically the distance from the reactants to the highest bump. So from this distance to that distance is the activation energy for the whole reaction. Because once you get over that, you've got enough energy for the rest of it because they're all lower. Okay? Sorry. So here's a reaction mechanism. How many steps are in this? 3 steps. 3 bumps, 3 steps. What's the EA for the overall reaction? Whoa. So we're going from 50 all the way to the highest bump, which is 30. Okay? Because if you only put in enough to get over the first step, that's 10 kilojoules. That's not enough to get you over the second step, right? What's the rate determining step? Step 2. Because this is 1, this is 2, there's 3. Which is the fastest step? This is kind of... Yeah, I would say step 3 too, but I'd make it way more clear on a test, okay? Basically the one with the shortest... that's not the one. The shortest activation energy is going to be the fastest for that step, okay? But I'll make it very clear. This is step 1, step 3 look fairly close, so we'll say step 3. Is this reaction endo or exothermic? Endothermic because we end higher than we start. Delta H is what? 20 kilojoules, 70 minus 50. Delta H for the reverse is, it'll be negative 20, right? Because it's exo going in the opposite direction. What's the energy of activation for the reverse? It's 10. Right? Sorry? You have a question 9? What's your question? Oh, the RDS? Oh, there it is. Apparently, the formatting on this is awesome. Question 9. What is the rate determining step for the reverse reaction? It's 2. It's the highest bump again, right? Step 2. Okay. Yep. Well, on a test, I'll make it very clear, but basically you're like, what is this distance? As opposed to this distance. Now, that's very, yeah, it's not this line, it's this, right? Because this is the energy of activation for the third step.
Oh, I thought that went up to 8.
Yeah, but also, like, they look the same to me. On a test, I will make it very clear, okay? It won't be ambiguous like this. And I guess if this was a test, if you said it's step 1 because this distance is smaller than this distance, I couldn't really argue with you. Do you know what I mean? If you explain yourself, then that's all I really care about. Okay? All right. Catalysts. So we've talked about catalysts. They change the activation energy. Why do they change the activation energy? Because why not? It's because they change the mechanism. Okay? So catalysts change the activation energy by changing the mechanism. They give you an alternate path, essentially. All right? So catalyst is an introduced substance. This is important because it's going to be different than a reaction intermediate. So we introduce or we add a substance which changes the mechanism. Okay? Because we're changing the mechanism, we lower the activation energy. Because the activation energy is dependent on the nature of the reactants. All right? So you have to change what the reaction is doing to change the activation energy. All right? Just for completeness, an inhibitor would increase the activation energy. Kind of makes sense. And I think I said it on Friday. Some books will say a positive catalyst, which would lower the activation energy, and a negative catalyst would increase the activation energy. I'm just going to say catalysts and inhibitors because that's self-explanatory, I believe. All right. So here's our reaction. The uncatalyzed reaction. This is hydrogen peroxide decomposing into water and oxygen gas. This is elephant's toothpaste, basically. If you have potassium iodide, it breaks it into a reaction mechanism that has 2 steps. The big thing here is, if we look at this reaction, OI minus, what is OI minus? This thing. What do you call it when it forms and then gets used up? This is a reaction intermediate. No, I wasn't looking for the name, sorry. It's a reaction intermediate. But if you look at I minus, doesn't show up in the overall reaction. Okay? It is added on the left side. So you are putting it into the reaction. And then it pops out at the end. It'll disappear inside of it, and then they pop out at the end. That's the definition of a cat. That's what a catalyst is. Okay? So a catalyst is added in, and then you get it back at the end. Now, it might be hard to pull it out of solution, but you can theoretically get it back in. An intermediate forms in a reaction step and then gets used up in the next step.
So it like matters like in the order in which it.
Yes. Reaction intermediates form first on the left, the right side. Catalysts will show up on the left side and then are spit back out on the right side at the end. Okay? Does that make sense?
Yeah.
Yes. Catalysts are on the left side first and then they come out on the right side. A reaction intermediate is on the right. They form on the right side and then get used up in another step. Okay? It doesn't have to be the next step. It just has to be some step, but it'll be on the left side. So a reaction intermediate is like right, left. A catalyst is left, right. If that makes sense. Okay. Okay, so this is what a catalyst does, basically. You have the uncatalyzed reaction. This is the normal potential energy diagram that we see. Big bump has an activation energy of 170 minus 60, so 110 kilojoules. So EA of the uncatalyzed reaction is going to be 110 kilojoules. You add a catalyst, it'll increase the number of steps. That's why we have a couple bumps here. But each one of those steps has a lower activation energy. Okay? So when you add the catalyst, the activation energy changes from, I'll call that 130 minus 60, so 70. 70 changes to 70 kilojoules. Okay? Why does that speed up the reaction? You're on the right track. You're like right there. So I know what you're saying. So it means this.
No, I have it. It's like more molecules for Is that right?
It's the same number of molecules.
But like there's like more.
You're close. So remember this graph? Remember this? This was threshold energy, right? And we had this many molecules pass the threshold energy, all right? When you change the mechanism, the threshold energy will change, right? So the threshold energy is going to move, I don't know where, just say here. So this is the catalyzed version. So now we have a higher percentage of molecules with enough kinetic energy to get over that hump. Okay? Does that make sense? So then you're both right in that there's more collisions happening and there's more effective collisions happening because there's more molecules past this. That's why lowering the activation energy helps you out. It doesn't matter the number of steps because each one of those steps will be faster than the uncatalyzed reaction. This is number of molecules, and this is kinetic energy. Everything's kinetic energy. All right. Are we okay? Yep.
Why does it lower the threshold?
It's a different reaction pathway. So you're not doing. Yeah. Threshold energy to break this apart. Like those two molecules would have to come together. Whereas if we add this, the iodine is going to bond in here and create an intermediate, which is a different molecule, I guess, for lack of a better term. All right. So that's kind of that's a good question because it's not this. Like I put them on the same graph, but it's not the same threshold energy because it's a different molecule. I just wanted to illustrate that you have more molecules past that point. Okay. Okay, so for a catalyst, Activation energy is less. More molecules can make it over the barrier, so the reaction speeds up. That's the graph that I was just showing you. Catalyzed reactions involve more steps, but it's the EA that matters, the activation energy. This is important. A catalyst does not change the potential energy of the reactants. It doesn't change what you form. So they end up in the same spot. If you look at the graph, all this stuff in the middle is different. We don't care. I mean, we care, but we don't care because at the end, we get the same products. If you're getting the same products, you have to have the same potential energy. Okay? So that's important. You don't go lower, you don't go higher. It just changes the bump in the middle. Okay? Oh, yeah. We always talk about, okay, if you do a reaction, this is the reaction that happens. All right? If you add a catalyst, it uses the catalytic pathway. That's all. Like, it's not a lie, but it's just putting blinders on. When you do a reaction, especially when you go on and you do organic chemistry and stuff, there's hundreds of reactions going on in there all at the same time. That's why you don't get 100% yield, because there's other reactions going on. So when you add a catalyst, the uncatalyzed reaction is still happening. It's just so slow that it's basically insignificant for us. Okay? Because it's so slow and it takes so long compared to the catalyzed reaction, we don't really care about it. Okay? But just be aware when you do chemistry, especially like when there's lots of molecules coming together, there's side reactions going on all the time. And one of the things when you go on in if you go on in chemistry, is you learn how to block out the side reactions to funnel a reaction so you get a higher yield. That's a big thing, especially if you go on to like, what am I trying to say? Like high production chemistry. The big chemical plant. I forget the word I'm trying to say. But when you're trying to maximize yield, that's a big, big important thing because it costs you money if your yield is low. All right? Industrial chemistry. That's the word I was looking for. Yeah.
So what you're saying is that when you add a catalyst, there's like a catalyst reaction happening, but there's still like that original reaction that's happening.
It's just super slow, yeah. Yeah. And then once the catalyst reaction happens, it grabs more of that. So it's like pulling, there's two reactions going on. The catalyst is going really fast, so it's like pulling all the molecules towards it, right? Even though like a few molecules happen, but all the other molecules that haven't reacted, the catalyst is just like, I'll take those.
So eventually the catalyst will react though.
Yeah, well, some might go the long way, but a very low percentage. Okay. If a catalyst speeds up the forward reaction, it also speeds up the reverse reaction. Okay? That's kind of implied by you have a lower bump. Okay? Lower activation energy. If it speeds it up going this way, you speed it up going the other way. I think that is it, people. There's the assignment attached to it. Remember, you have a quiz tomorrow. What would be a nice question for me to put on your quiz tomorrow?
Find the missing space.
There you go.
I literally did not hear a single thing you were saying.
One sec.
You were talking about